Hi, everyone, and hi, Ashley and Cindy, who said hello in the chat. Can you guys see me and hear me okay?
Yes.
Okay, great, thank you. All right, so as we're getting started and as people are joining, I've put up some things for you guys to think about as usual, so go ahead and be thinking on your own for a couple of minutes about how many total carbon atoms are in each of the following molecules. Hopefully you guys reviewed the slides from Wednesday. Remember, I told you in class that there was going to be a slide deck, a portion of that slide deck that you guys were responsible for reviewing on your own. So hopefully you did that, and hopefully you'll all be able to answer the question up on the slide now. So take a moment and think about that, and then we'll look at it together. Okay, who wants to give this a shot? Pick a molecule and let me know how many carbon atoms you think it has. All right, we've got a 4 in the chat box. I assume that's for the molecule on the left. Yeah, all right. So we've got 4 carbon atoms in the one on the left. And how about the one on the right? How many in that one? 6. Perfect. So this molecule here is actually butane, just like butane fuel, butane gas, butane torches. You guys don't need to know that name right now, but that's coming. That's going to be a name that you will need to know in a future chapter. And this molecule here on the right has 6. So how did we get to this? Well, these structures are drawn in what's called line angle format. And in the line angle format, at the end of every bond that's shown, unless there's another atom shown, like we have here where the oxygen is shown, otherwise that end of the bond can be assumed to be carbon. So we have a carbon here, 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 and here. If we were to draw out that full Lewis structure, it would look like this. So in addition to each carbon, each end of a bond being assumed and understood to be carbon, every carbon, unless you have some reason to think otherwise, some drawn in lone pair or a drawn in formal charge, unless you have some indication otherwise, you get to assume that all of the remaining valence shell of carbon is filled up by carbon-hydrogen bonds. So what do I mean by that? We've talked already about how carbon likes to have 4 bonds associated with it. So the carbon that I have my laser pointer over right now has 2 bonds already accounted for that are participating in bonds to other carbons. And that means that there are 2 bonds left over to get it a full octet, and those 2 bonds are bonded to hydrogen. So you can see that represented in the full drawn out Lewis structure down here. This is the carbon we were talking about. It has 2 bonds to carbon. Those are shown here and here. And then it has 2 implied hydrogen atoms. So all of these, there's 10 hydrogen atoms in this molecule, and they are all implied in just this simple structure. So you guys can see how much faster it is to draw line angle drawings than it is to draw Lewis structures. So that's why organic chemists do this. We also do it as organic chemists because it helps the interesting features of molecules stand out. Nobody likes these boring carbon atoms that have full, like, hydrogen atoms filling up all of their spaces. Everybody likes exciting, new, different things like this carbon-oxygen double bond or this carbon-carbon double bond here. So all of this is covered in chapters 110 and 111, which I'm going to encourage you guys to revisit if you didn't already. And we'll take just a brief time today to kind of cover the slides from last time in short summary format. All right.
I'm late. Can you tell me what we're doing just briefly?
Yeah, these are just brain exercises. So we figured out how many carbon atoms are in each of the following molecules by applying the line angle drawing rules that we learned about, that you guys would have reviewed after class last time by looking at the slides. And there will be a summary. We'll go over them again a little bit later. So you can think about this on your own. Okay. So you guys are, did you have another question?
No, I'm good.
Okay, great. You guys know who I am. You know how to get a hold of me. I really hope that by the end of the day today, I'll be caught up on emails, and please poke me again if it's something urgent. Otherwise, thank you for your continued patience, and I promise it'll get better as the semester goes on. Your Achieve Chapter 1 homework. Originally, I had it scheduled to be due on Monday morning, but we are not going to finish the chapter today. So my hope is to finish the chapter on Monday, and your homework will be due on Wednesday. I don't really recommend waiting, though, because you can get a lot of your homework problems done with what you guys already know, because we're more than halfway through. We will also be having a quiz on Chapter 1 next week. I'm targeting Wednesday in class, and we'll talk a little bit more about that on Monday, but just be prepared for that. Someone's asked in the chat box if the date is updated on Canvas. I did just before class started, so it might not have refreshed on your end, but it should be updated in both Achieve and Canvas, I think. If it's not, you can let me know. And also, I've been posting a slide like this at the end of the slides, but I wanted to make sure that you guys noticed at the end of every slide deck, I post a kind of a summary of the chapter. And on that summary page, it reminds you that there's also practice problems from your book that are posted on Canvas. So I just wanted to pop up the screenshot and be abundantly clear about this. So this is under the modules section of Canvas. And in the same place where I post the slides, I also have posted a set of kind of targeted practice problems from your book. Now, these are ungraded. They're for you to do on your own. I'm not going to go over them. But what I've tried to do, because there are a lot of problems in your book, lots of problems throughout the chapter and in the back. And what I've tried to do is pull out and kind of target you towards a couple of problems for each topic. And so you'll be able to see that if you click on this link here. That doesn't mean that you shouldn't do more problems from the book. So there's a lot more problems in the book than what I've pointed out. And especially for particular areas, if you're struggling with a concept, if you're just wanting more practice on a concept that you feel confident in, there's no bad problem in your book. I just wanted to kind of help kind of guide everybody. And you're welcome, Ashley. All right, so here is where we're at with the chapter. You can see we're more than halfway done. The meat of the chapter is right here. So even though it looks like we have a long way to go still, this won't take as long to cover. We are going to come back and touch a little bit on these previous topics since we kind of didn't quite get all the way through resonance at the end of class on Wednesday. So let's go ahead and do that. We're going to start off by reviewing where we left off, picking up right where we left off. So hopefully you guys remember from last time, but now we know enough from what we've learned so far in the chapter to understand that a complete Lewis structure is going to try to fulfill the octet rule for as many atoms as possible. It's not going to break the octet rule for any atoms, right? We're not going to have any atoms with more than 8 electrons, no 10 electron atoms. It does need to have the right total number of electrons. So it needs to have the number of electrons that came in as valence electrons of the atoms involved in making that molecule, and then plus or minus the number of electrons associated with the overall charge of the molecule. And remember, if it's a negatively charged molecule, that means it has to have more electrons. And if it's a positively charged molecule, it'll have less electrons. And also, we know that a complete Lewis structure has to show all formal charges that are non-zero. So I get a little sloppy in writing it on the slide, but any formal charge that is not a zero needs to be shown on that molecule. We also began last time talking about resonance forms, which basically is a tool that chemists use to make sure that we are really looking at the different possibilities for how the electrons might distribute themselves in a molecule. So there are some compounds where it's not just one way of distributing the electrons. There are some compounds where we could draw more than one valid Lewis structure. And so that's where resonance forms come into play. By definition, in a Lewis structure resonance form, we're only allowed to move the electrons around. We can't move any nuclei, so you can't rearrange bonding order. You can only move electrons. And we talked about how if you have these resonance forms, the true structure is going to be some kind of average of those resonance form, possibly a weighted average if one of them is a more major contributor, but it's going to lie somewhere between or among all of those forms. Jaden, do you have a question?
Oh, no, sorry. I'm trying to turn my mic off.
Okay. All right. So this resonance structure idea can be shown in all sorts of different examples, but what I'm showing here is formaldehyde. I showed you guys this on Wednesday also. And formaldehyde is a good example of a molecule where there are more than one Lewis structure. So it has resonance forms, but not all of these structures are always equal. So we talked about on Wednesday how this resonance structure on the left is a major contributor because all of the octets are filled. We can also draw a reasonable Lewis structure, shown here on the right, where the electrons from this double bond move up and become a lone pair. Of course, it's still going to leave behind a single bond, otherwise we would have messed up our molecule. When we do that, we create two formal charges, a negative formal charge on the oxygen and a positive formal charge on the carbon. You also notice that carbon no longer has an octet. Now carbon only has 6 electrons, whereas before it had 8 electrons. So this structure on the left is the more contributing structure to what the molecule looks like and acts like and behaves like. However, this secondary structure does give us information about reactivity, and we'll see indeed as we get further in the course that carbon-oxygen double bonds always do behave with a little bit of this kind of a resonance structure contributing to their reactivity. So we talked a little bit about this right at the very end of class last time, so I want to drive this point home. We decided to take these double bond electrons and move them up to the oxygen. Could we have moved them down to the carbon? Well, the answer to that is yes. Technically, we could take those multiple bond electrons and move them down to be a lone pair on the carbon. We can do that because we would not have broken any octets, so it is allowed. But when we do that, we create a negative formal charge on the carbon and a positive formal charge on the oxygen, and that's not great. Okay. Someone in the chat has asked, are the major and minor contributors only in cases where there's a dipole moment? No, we're going to go through different rules where you can see for major and minor contributors. So just hang on to that question. I think it'll be answered over the next couple of slides. Okay, so if we were to take these electrons and move them down to the carbon, carbon would carry a negative charge, oxygen would carry a positive charge. Can you guys all make sure your mics are off? Great, thank you guys. Okay, so what do I mean by where those formal charges are located? If you have negative charge buildup, so a negative formal charge, that negative formal charge will be more stable on a more electronegative element. And of course, the converse of that is also true. A more electropositive element, so hydrogen, carbon, will be better able to stabilize a positive charge. So that's why the Lewis structure for formaldehyde that has these two formal charges separated out in this way is better than if we had taken that lone pair that used to be a double bond and put it on the carbon. So hopefully that makes sense. We're going to look at another couple of examples, and then I'll give you the priority set of rules. And again, all these slides were posted from Wednesday, and they'll be posted again today. So electronegativity is important in determining this stability of formal charge concept, but it'll really play a role throughout lots of different activities that we do in this class, so just keep that in mind moving forward. Okay, what do you do if you have two resonance structures where all of the octets are satisfied and they both have a negative charge? How do we decide which of these is better? Well, we apply the rules we just talked about on the last slide. Which element is more electronegative, oxygen or nitrogen?
Oxygen.
Great. Oxygen is more electronegative. It is further to the right on the periodic table, so that oxygen is better able to stabilize that negative charge. So what that means is that the resonance form on the left here is the major contributor. The resonance form on the right is the minor contributor. So hopefully that makes sense to everybody. All other ways that you would use to distinguish these two are equal. Here's another example. In this example, we have a resonance form where all of the octets are satisfied and there are no formal charges anywhere. And we also have a resonance form where all of the octets are satisfied, but our electronic distribution means that we have a formal charge that's negative on this oxygen at the end of the molecule and a formal charge that's positive on the oxygen in the middle of the molecule. So you can see kind of, and hopefully you can feel just intuitively that this one on the left without any formal charges is the major contributor. The one on the right also contributes, and it does tell us something a little bit about the reactivity, but it's a minor contributor because the formal charges are not minimized. We also ideally want to be able to have the smallest separation
again, please.
of formal charges. Somebody wanted me to say it again.
Yeah, I'm a bit confused.
Okay, so let me back up, get rid of that. What a more stable resonance structure is going to be the major contributor. And so in the case that I'm showing you here, the major contributor, which is also the more stable one, is the one with the minimized formal charges. Hang on. Okay, so what I mean by this is that in the compound on the left, there are no formal charges anywhere on the atoms in this molecule. In the compound on the right, I'm saying compound, these are the same compound. In the resonance structure on the right, the electronic distribution is such that there's more electrons shifted down to this oxygen. So this oxygen down at the end has 3 lone pairs, and the oxygen in the middle only has 1 lone pair, still has a satisfied octet because it has a double bond to nitrogen. But what that means is that the oxygen atoms, both of them on the right here, are carrying formal charges. And that makes this resonance form less stable and more of a minor contributor. Okay, you're welcome. Okay, so we also, just in general, in addition to minimizing formal charges, we want to try to keep those formal charges, if we have to have them, if there's no other way around it, we want to keep those formal charges as close together as possible, right? So in this case down below, this is sulfuric acid. And what I'm showing you on the far left here, we have a resonance structure we can draw that has no formal charges. And indeed, that's going to be the best resonance structure. The worst resonance structure, or the least contributor out of the ones that I'm showing here, is this one all the way on the far right, where we have negative charges on 2 of these oxygens. We've basically taken both of our double bonds and moved the double bond up to be a lone pair on the oxygen. And so when we do that, we leave a +2 charge on the sulfur. Okay, so I'm going to pause here for just a moment and let you guys know I have broken the octet rule for sulfur, right? That sulfur has 2, 4, 6, 8, 10, 12 electrons around it. And I've told you guys in this class, we're not going to break the octet rule. So here's the deal. In row 2 of the periodic table, so the row that includes carbon, in that row of the periodic table, you cannot break the octet rule. The octet rule is actually a rule that is hard and fast, and you can't go beyond 8 electrons for those row 2 elements in their valence shell. When you get down into row 3, because the 3p orbitals are high enough in energy, those 3p orbitals are actually close enough to the 3d orbitals that the elements in the 3rd row can, on occasion, very rarely, break the octet rule. So for the purposes of this class, my class, I'm not going to ask you about breaking the octet rule, and sulfur is probably the most common example of an element that does this, but any of the 3rd row elements can do it. For my class, in this course, we are going to stick to 2nd row elements where you have to keep the octet rule, right? Not allowed to break the octet rule in my class. I'm showing you this as an example though, because not every orgo professor does this. Some orgo professors routinely throw sulfur into the mix and routinely ask that you guys remember and know that sulfur can break the octet rule. So I do want to make you aware of it. Potentially it'll come up in your future courses, but for my class, I'm not going to ask you any weird breaking the octet rules. For us, we're not breaking the octet rule. Okay, so someone has asked if I can explain the difference between the middle two configurations. So these two resonance structures in the middle, they're identical to each other in terms of their energy or their stability. So the amount they contribute is the same. They're different only in that, remember, for resonance structures, we're not allowed to move around any nuclei. We have to kind of designate each atom to be where it is, and we can't move it. So all we're saying is that there are two different oxygens attached to the sulfur that are just oxygens without a OH, right? And so sometimes that negative charge could be on one and sometimes it could be on the other, but that's the only difference between the two middle configurations. Hopefully that answered your question. Abby, you asked me to include a note on that in the slides, please. It would be cool if you could send me an email. I don't mind putting a note on the sulfur and the not breaking the octet rule stuff, but I won't remember. So if you could send me an email, Abby, I would appreciate it. You're in charge of that, and I will update that slide before I post. Perfect. Thank you, Abby. Okay, so this is where we are with resonance structures and formal charges, trying to be minimized and trying to keep them close together as much as possible. Now, I just want to take a moment to put all this stuff together and tell you, basically, for thinking about resonance structures, you need to think about the following in order of priority. These are going to be the rules that you follow if I ask you, what's the major contributor of this set of resonance structures? First and foremost, look to see which has as all of the atoms octets full, right? So if you have a case where you have one that has all the octets full and another one that doesn't, go with the one with the full octets. Okay. Next, if that doesn't help you find the one resonance structure that's the most major contributor, check and see if one has more overall bonds than the other. They all have the same number of electrons, right? But electrons that are living in bonds are going to give stability relative to electrons that are living in as lone pairs. If all of those things are equal in all of the resonance structures you're looking at, and you can't differentiate a major contributor, then you start looking at formal charges. Is there a negative formal charge? And if there is it on the most negative, electronegative atom? The flip side of that also is true. Is there a positive formal charge? And if there is it on the option with the most electropositive atom? And then finally, just like we saw on the last slide, we want to minimize the formal charges and we want to keep them as close together as possible. So we want the formal charges to have as little charge separation within the molecule as possible. So most of the time you won't have to go through all four of these rules. Most of the time, rules 1 and 2 will be enough to get you to the right answer. But if they're not enough, then you need to start looking at formal charges. All right, you guys have any questions about that? Okay, so let's do a sample problem together. I posted this on the slides on Wednesday. Did anybody try it? Yeah, no, probably not. Let's try it together. What I want you guys to do is show me the important resonance forms for this molecule. So CH3OCH2 with an overall positive charge on the molecule. You're not going to have to upload this problem. This is just for us to do together, so you don't have to worry about uploading for this one. So once you have your important resonance forms drawn, then you need to think about them, look at them, and decide which of them is the major one and which is the minor one, or are they the same? So the way I've already been talking, I'm hinting to you that there are two because I keep saying which, this or that. But go ahead and try it on your own. And of course, in order to get started on these resonance structures, my recommendation is that you guys draw one Lewis structure. Draw just one Lewis structure that is valid and legitimate according to the molecular formula and overall charge that you have on this molecule. And I've given you a hint here. I've told you that the atom arrangement is linear, COC, and then hydrogen atoms are all attached to carbon atoms. So once you draw your one Lewis structure, look at that Lewis structure and see if there's any electrons you can move around to get another resonance form for that molecule. Okay, how are you guys doing on this? You guys ready to talk through it together? Thank you, Ashley. All right, so I'm gonna put up one resonance structure that is one of the ones I came up with. This is the first one that I drew. So you can see we've got the right carbon atom arrangement, carbon, oxygen, carbon, H atoms attached to the carbon atoms. And it's an overall positive charge, which in the resonance form that I drew, that formal charge lies on the oxygen because I have a carbon-oxygen double bond, which means that oxygen has a valence number of 6 minus the 5 things that are distributed around. So oxygen is carrying the positive charge. How would you take there's another arrangement of electrons here. So what electrons are we allowed to move? We only have 2 choices here because we can't move any of the single bond electrons because then we'd be breaking bonds. We can move this lone pair somewhere, or we can move the double bond portion of the carbon oxygen. Great, we've got people in the chat box who are saying the double bond. That is the best thing to do because technically here, we can't move this lone pair, right? From this resonance structure, if we try to take this lone pair and push it towards the carbon, we'd be breaking that carbon's octet in either direction. So we can only move the double bond. So the other resonance structure that we can draw looks like this one, where the oxygen has single bonds to both carbons and 2 lone pairs, and therefore that oxygen has a formal charge of 0. And the carbon that used to be double bonded to oxygen here, it gave up those electrons. So now it only has 6 electrons and it now has the positive formal charge. Remember, carbon has a valence of 4 and this carbon has 3 things attached. So now it's got the positive charge. So which one of these 2 resonance structures is better? So somebody said the one on the right is major. Well, let's see if you're right. Yep, right. Okay, so the one on the right is the major contributor. And there's a couple of different ways that we can use to look at this, but this is a little bit tricky. But the very first thing we want to do is make sure that the octet is satisfied for all of our atoms. And that is true for the contributor on the right. If you look at the carbon here in the molecule on the left, that carbon only has 6 electrons. So it's not breaking the octet rule, right? But that carbon hasn't fulfilled the octet. It doesn't have a full valence shell. And Ashley, if you're about to ask about why is it okay for an oxygen, which is electronegative, to carry the positive formal charge? Hang on, but if it's something else, go ahead and ask.
No, I was gonna ask about what about the ion, the positive charge? Isn't it supposed to be on the outside the bracket?
Okay, so that's a good question, Ashley. Have the positive charge outside of the bracket. All that means is that we're not specifying where in the molecule that positive charge exists or resides. So because we have put that formal charge, we have said in this one on the right, it is on the oxygen. In this one on the left, it is on the carbon. When we tell exactly where in the molecule that positive charge is, it stays in the molecule and not outside of the brackets.
Okay, thank you.
You're welcome. Also, the brackets here actually are not the same brackets that you use for a complex ion, just to make things even more complex. The brackets here are often designated to show these two resonance forms are actually the same molecule, and so they're in the brackets. You guys don't have to worry about drawing brackets for me, but I would like for you guys to know and recognize this type of an arrow indicates resonance forms. Okay, so to go back to what I was saying about this oxygen atom over here, right now this oxygen atom has a positive formal charge on it, but oxygen is electronegative. So it is true that the positive charge would rather be on a carbon than an oxygen in general. That's a generally true statement, but the resonance structure rules tell us that it is more important that we satisfy the octets. So that's why we have the right resonance structure as the major contributor. Okay. And this note on the bottom just says what I just said out loud. Okay, so that's all we're going to do for resonance for the moment. I'm going to take the next couple of slides and do a very quick summary of the slides from last class posted lecture on chemical formulas that correspond with sections 1-10 and 1-11 in your book, just because I want to draw out and point out a few things. So hopefully you guys read your book and reviewed the slides and know all about condensed structural formulas. One of the things that I want to point out is that these condensed structural formulas, which are shown to the right here for each of these Lewis structures, what they do is they give us information about how the bonds are connected. Okay, so the bonds are connected in such a way that these three carbons, so there's three of them because there's CH3 groups and there's three of them, these three carbons are attached to this carbon next to it. So when you're looking at condensed structural formulas, you can generally assume that the hydrogens you're seeing are attached to whatever the atom is that's just to the left of it, and that atom is attached to whatever's to the right of those hydrogens. So that might have sounded awkward with me explaining it, but I think if you see enough examples, it'll become intuitive. So in addition to connectivity mattering, you need to be aware that structure is implied because all chemists everywhere know the Lewis structure rules and they know the octet rule. So if I show you this structural formula, this condensed structural formula, instead of this condensed structural formula where I'm showing you that there's a double bond, notice that the information is the same in both of them. It's the same CH3, CH, CH, CH3. Okay, so if you are a chemist anywhere in the world, you would look at this one on the left, and even though it doesn't show a double bond, you would know that that double bond exists between those two center carbons, because otherwise they wouldn't be bonded to enough things, right? So everybody remembers, right, that carbon likes to have 4 bonds. But if we look at carbon, the second carbon in this molecule where my laser pointer is, that carbon is bonded to a hydrogen, that's 1, bonded to another carbon in this direction, that's 2, and then it's bonded to a carbon in this direction, that's 3. Because this is only one hydrogen, that clues us into the fact that there is a fourth bond that is actually a double bond to that carbon next door. So these are all implied in the structural formulas, whether it's written out or not. You'll get to know this by looking at trends and hints like as you go along the way, and the more examples that you see. So someone has asked, could the third option have had CH2 in the middle to further condense the formula? I don't think so, because there's no CH2. If you're talking, John, about this molecule, there is no CH2, right? That carbon is just a CH, and this carbon is just a CH.
I meant, since there are two CH1s, could they have, like...
Oh, I see. Technically, I guess that would be okay, but nobody ever does it that way. So
okay,
it's not technically wrong. It's just not as intuitive to organic chemists, because the CH is kind of a signal that double bond is there. And so technically it's not incorrect. I've never thought of it that way. So right on for creativity. But in reality and in practice, people just don't do that. All right. So another example I wanted to pull out from the slides from before is to point out the distinction between, if you see an oxygen in the molecule, there's really only two different patterns that oxygen is going to go in. It might go in carbon, oxygen, carbon in kind of a linear fashion, or it might be kind of outside of the linear chain as an oxygen double bonded to a carbon. And how do you know the difference? So in the case of carbon, oxygen, carbon in a linear fashion, you can tell that because if you look at the carbon to the left, that carbon to the left has some other things attached to it, right? It has some hydrogens attached to it in this case. Whereas if you look down here, I actually can't get my laser pointer to go down there because a pop-up keeps happening when I do. But if you look down here at the bottom, to the left of that oxygen is a carbon that doesn't have anything else attached except for whatever's on the left of that. So that's the distinguishing feature that helps you to see and get to know that you have a COC versus a C with the O double bonded kind of outside of that little stretch of linear carbon atoms. This is probably one of the hardest things for newbies at this to see. I'll try to explain it one more time, but it honestly might just be you guys needing to practice it. But it's very hard. It's very tricky to see. But if we look at this oxygen here in this COC coordination pattern, we look at the carbon that it's bonded to, and that carbon that it's bonded to is already bonded to three other things, right? It's bonded to a carbon over here and two hydrogens. So because this carbon is already bonded to three other things, it can only have a single bond to that oxygen. If we look down here, here's the oxygen. If we look at the carbon to the left, so the carbon that the oxygen is bonded to, that carbon is now only bonded to one other thing. It's the carbon to its left. And so because that carbon is, well, actually, it's not actually bonded to just one other thing. It's bonded to that one thing on the left, but there's nothing else showing that it's bonded to, to the left, which means that it has enough, I'll call it open valency to accommodate a double bond to the oxygen. Okay, but now let's think about that. Once we put a double bond to the oxygen, we've got the double bond to the oxygen, that's 2. We got the single bond to the carbon on this side, that's 3. So it still needs a fourth bond, and that is on the other side of the oxygen, all the way to that carbon over there. I know it gets confusing. I know it's not intuitive, but it is what it is, and it's organic chemistry, and you'll get it with more practice. Okay, next thing I want to cover is to take a couple moments and talk about these line angle drawings. These line angle drawings, as I talked about and mentioned in the beginning of class, we're going to do a couple of things, and this is going to help us as chemists draw molecules quicker and see the cool parts of molecules more readily and more quickly. The first thing we can do is anytime we've got hydrogens attached to carbon atoms, we're going to make them invisible. Every chemist knows that carbon wants to be bonded to 4 things. So every chemist is going to look at a carbon atom in a line angle drawing, count up how many things that it's bonded to, and recognize that every other bond that gets it to 4 is filled by a CH bond. So we're going to get rid of all these hydrogens. We're not really getting rid of them. They're still there. We just are not drawing them out. They're implied. Then we would be left with this series of carbon atoms connected by bonds. And that's a lot of carbon atoms. Carbon is the central element of organic chemistry. So it's just too many carbon atoms. So what we're going to do now is, instead of writing out carbon atoms, we're just going to know. We're just going to all remember that at the end of every bond, there's a carbon atom. So just like there's 1, 2, 3, 4 drawn out here, here's the end of a bond. So we have 1, 2, 3, 4 carbons here. Okay, a couple more rules we need to cover for line angle drawings. If we have other hydrogens in the molecule, so for example, hydrogens attached to a nitrogen or an oxygen or anything else, we have to show those. They're going to become participants in reactions later on, so we need to know explicitly whether they're there or not. We also need to show, I'm sorry if you guys can hear whatever construction is going on behind me. We also need to show any element that is not carbon or hydrogen. Any of those atoms we have to show. Okay, this line angle drawing thing, this is the most common way to depict organic molecules. And this is something that you guys for sure need to get comfortable with seeing and also need to get comfortable with drawing. So we know you guys are new to this, so we don't expect them to be perfect and pretty. We do expect them to follow the rules, though, and the rules are laid out here. All right, so your book has all sorts of charts. It's a really good idea to do this comparison on your own and look and see if the condensed structure makes sense to you looking at the line angle formula. Don't forget these ends of the bonds are carbons also. If it helps you, you can number your carbons. You can actually literally write under here 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so yeah, take a look at that. And then of course, every hydrogen attached to anything that's not a carbon, you have to show. Okay, we're almost there. Whew. Chemical formulas and molecular formulas. So we've been talking about condensed structural formulas, which look like this for butane 1-ol. Don't worry about that name for right now. But there's another describing this, and that is through the molecular formula, which just tells us literally how many of each element. So I want you to notice, though, how much information there is stored in this condensed structural formula and how little information there is in this molecular formula. Of course, it's still information, but we lose a ton of information when we go from a condensed structural formula, which gives us information about how these things connect, to this molecular formula. And also I want to point out, there is not just one way to arrange the atoms in this molecular formula, right? The condensed structural formula, I know that all 4 of those carbon atoms are in a row and that the oxygen atom is after that. In this molecular formula, I have no idea. They could be branched. The oxygen could be on the second carbon. This does not tell us or specify. So we have multiple molecules that could fit this definition. The empirical formula is just the ratio of the elements as opposed to the molecular formula, which is the actual element count for each molecule. We will almost never use the empirical formula in organic chemistry, but I didn't want to leave it out. The empirical formula can sometimes match the molecular formula. So that's something else to be aware of. And one thing that you guys will need to be able to do for this class, and this goes back more to the line angle drawings, you need to be able to count and see the implied hydrogens. You need to be able to look at this molecule, and in looking at this molecule, you should be able to visualize. So for example, how many hydrogen atoms are attached to the carbon where my laser pointer is? 1. Nope, just 1. So how many bonds are showing? We're showing 1, 2, 3 bonds because we have a double bond here. That means there's only a 4th bond left, so 1 hydrogen here. How many hydrogens on this carbon?
2.
Great. All right, how many hydrogens on this carbon here?
None.
Zero. Zero. How many hydrogens on that oxygen? Zero.
None.
Yeah,
Zero.
there are none, because the rules tell us if we're doing line angle drawings, we have to show those hydrogens if they're on an oxygen atom. Okay, awesome. So we've covered all the way through here. I want to do some practice problems. There's going to be an upload for this. We're not going to get to anything else, so we're going to be a little behind, but that's okay. We'll figure it out. We'll catch up. I want to comment that these kind of four in the middle here, octet rule, Lewis structures, formal charges, and resonance, those four are the most important concepts in this chapter, I would say, and they'll underlie a lot of what we do for the rest of the course, not just the rest of the chapter, the rest of the course. So with that in mind, here's some more practice for you guys. I'll be here and sticking around so you guys can ask me questions as you go through this. If you want to work on this on your own and then upload it, it's due by 11:59 p.m. today. So you can take a screenshot and you can do it now or you can do it later. I'm going to get up and turn on my lights in the room here. And then after that, I'll be happy to talk to you guys about whatever you want to talk about. But this is it for today. This is where I'm going to stop. And you guys can just work on this now or later. Just make sure you upload it by 11:59 p.m. for full credit. And Asher, no, there were not upload problems for the last class. There were a few practice problems embedded within the slides for you to practice and do on your own, but not an upload. And Brenda, I do not right this semester, I'm not teaching Orgo 2. I'm only teaching Orgo 1 this semester. And we haven't done scheduling for next semester yet. So I don't know if I'm going to teach it next semester or not. All right, let me turn the lights back on and then I'll be.
So I got a question about
Yeah, go ahead. What's your question?
Oh, I got a question about my the what I call it, I achieve the AQ for some. Like I did email you yesterday, a couple days ago. I mean 2 days ago. I emailed you about that. I'm trying to find it, but I didn't see it.
You're the one with the course code, right?
Yeah, correct.
Okay. If you look, so the course code can be found in two different places. The course code is found in the front of some of the slides that I posted recently. So I think on class.
I'm trying to find on syllabus and no, it's the modules.
The course code's the course code's not listed on the syllabus. If you go to the posted slides, I believe for lecture 2, and look in the first couple of slides under the announcements, the course code should be there.
Announcement? 1 second. Let me try to check this. I'm trying to find it but I didn't see it. I don't know where is it.
Okay, are you able to see the posted slides on Canvas?
Yes, I believe it. Oh, okay, you talk about an announcement detail, right?
I'm not talking about the announcements tab in Canvas. I'm saying if you go to the slides that are posted.
A slide.
The modules, under the modules. Okay, gotcha. And okay.
Got it. I'm sorry about that.
No, that's okay. If you still can't find it, another email, okay?
Oh yeah, thank you. I appreciate it.
You're welcome.
Thank you.
Yeah. Okay, Karina has asked in the chat box, what did you mean by charge separation in the order priority for resonance structures? So I'm going to try to do this verbally without moving the slides, Karina, but I'm not sure how well I'm going to do without pictures to point at. So when we talk about formal charges, each formal charge is associated specifically with an atom within a molecule. So if you have formal charges, say you have, just for an example, say you have a positive formal charge and a negative formal charge in one structure, it is more stable if those are on atoms next to each other as opposed to on atoms farther apart in the molecule. Did that answer your question, Karina? Great, thank you. You're welcome.
Professor?
Yeah.
I had a question about the line bonds that you said that we have to start making.
Yeah, the line angle structures, yeah.
Right. So you had showed us, one of the slides had the diethyl ether on it. So how would we draw a line structure for like that oxygen that'll be in the middle of two of the carbons?
Sure, great question. That oxygen will have a line on either side of it, and that would represent, each line would represent a line towards a carbon atom bond. I'll actually go ahead and draw one on here, so everybody who might be still sticking around and is looking at these slides, I'm going to draw over here in this box, but it has nothing to do with these practice problems. All right, so Ava, am I saying your name right?
Yes.
Okay, hi Ava. You're asking me about how to draw the line angle version of this molecule, diethyl ether, is that right?
Right. Yes.
Okay, it would look like this. Kind of looks like a spider.
Oh, okay. But
Okay.
the ends that are pointing towards the oxygen do not have carbons there.
So, right, because there's an oxygen here. So I your confusion, but the more you practice, I know I keep saying there's nothing else that I can say about that. Yes, so anytime you have a line, it represents a bond, and there's no other element listed at the end of that bond, then it's a carbon atom. But if there is, then it's whatever that atom is.
Okay, all right, that makes a lot of sense. Thank you.
You're welcome. And someone's asking about oxygen lone pairs. I was just about to say that. Oh, actually, this is a different question. Yeah. Okay. So let me come back to this one for a second. For the actual in-class participation problems, for this resonance structure problem here, when you look at a compound, you need to start looking to see if it has all of the lone pairs that you expect. So, Akila, hopefully I'm saying your name correctly. There should be lone pairs on the oxygen in this structure. It's not incorrect that they're not here in this case because, well, yeah, I didn't specify that we have to show all the lone pairs. It's a good idea for you to draw those lone pairs in, but it doesn't mean that they're not there because we didn't show any formal charges on it. But yes, those two lone pairs exist. Okay, and then Raven asked, the line over the lone pair is negative for the resonance structure. Yes, Raven, that's right. So if you look, that negative, that line over that lone pair is a negative formal charge, and that should make sense because carbon has a valence of 4. So if we have the valence of 4 minus the 5 things that are around it, then we have a formal charge of -1. And Akila, you're welcome.
I have one question about the Lewis structure.
Yeah.
For this one, like I know how to draw it, but I wanted to make sure, like, does that plus sign right there means that it has to be a positive charge on the hydrogen or just overall?
No, it's just overall. And if I was being more careful and exact, I probably should have put some brackets in here so that I didn't confuse anyone. But this just means the overall molecule has a positive charge associated with it. Once you draw out the Lewis structure, you'll find that it's not on the hydrogen.
Okay, that's because I was like, oh man, I think I'm doing it wrong because I'm not getting that. But thank you.
You're welcome. And Jayla, is that right? Has asked about posting the answers to the in-class problems. I'm not going to post them right after the submission closes. So it's going to be variable about when I post the answers to these, but they will always be posted with enough time for you guys to review them before any exam or quiz or test would happen, if that makes sense. So there's a deadline associated with the submission. And if you put your upload in before that deadline, you'll get full credit. If you miss that deadline, but you get your submission in before I post the answers, which will be at some point, my schedule gets a little crazy and hectic, as I'm sure you guys all experience with your own schedules. So because the in-class practice problems don't come on a regular schedule necessarily, I don't post the answers on a regular schedule either, but I will always post the answers for you guys with enough time for you to review them prior to some kind of a quiz or something like that. Did that answer your question? Okay, you're welcome. All right, guys, I am gonna jam unless anybody has any more questions.
Hello, Professor. This is Jessica. I believe I sent you an email. So hi. I believe I sent you an email after last class when you mentioned about the submission for the in-class participation. I had missed the first one, but I was hoping to do it for partial credit. However, I missed that class. So I was wondering if you had uploaded somewhere so I can do it and submit it for partial credit, please.
So for the last participation?
No, we didn't have anything last class. Like the one that I missed, it says June 24th, please.
Yeah, so that one was
January, sorry.
Yeah, that's okay. I'm sometimes living in June or wish I was living in June. For that one, it should still be open. You should still be able to go to it.
Yes, but I don't have the questions, please.
Oh, they're embedded within my slides from that day.
Oh, so I'll find them on the models.
Yeah, so if you go to module 1 and
then go for the class of the 24th.
For the class on the 24th, they're in those slides.
Sounds good. Thank you so much. Thank you.
You're welcome. Okay, guys, have a great weekend, everybody, and I will see you on Monday.
Professor, I have one quick question before.
Yeah, go ahead.
When the resident instructor is saying whether they would have the same energy or not, that depends on the major and minor, correct?
Yeah, it's kind of two different ways of saying the same thing. The major contributor is going to be the most stable and the least energetic.
Okay. All right. Thank you very much then.
You're welcome. All right, guys, take care. We'll pick up on Monday with